crooked again. What the heck? Why is my screen always crooked? Oh, what the heck? Come on. Always crooked. Calm down, Alex. It's gonna be okay. Sure, that works. Good morning again, Kyle. Hey, Itamar, Kihao. No, we're going over mechanical waves in the Regents class, so not light waves. After mechanical waves, we will go into light, but we gotta do mechanical waves first. Yeah. So I just gotta retool my brain a little bit from talking about metaphysics to physics. I'm so sleepy right now. It's a problem. Who are you, Wahoo? Identify yourself, please. Yeah, who are you? It's 10:37, but we still only have 6 people, so let's wait until 10:40. Okay. They're expecting a. Oh, really? Okay. Let me email the class. I thought if you're subscribed, you get a notification. I thought you get a notification if you're subscribed, whether if I'm like starting a stream or something. But whatever, let's email them. Oh. Yeah, okay, so let's just wait a little. Sorry, I know I said 10:37 and then I said 10:40, but I just sent the email. So let's wait. Yikes, 10:45. Guys, go to the bathroom, relax, lay on the couch, but be ready to learn at 10:45, okay? Sorry about the delay. Hey, Sarah. Good Hi, Tune. Good morning, Chris. Good morning, Becky. You guys are late. All right. Good morning, Caitlin. Good morning, Yona. It's all right, Ayanava. Okay. Cool. Now we have 13 people. I know I said 10:45. Let's get started right away. Okay. So the basic problem is pretty straightforward. Okay. Right. Excuse me. Cool. Whoa. What is this? Thought I drew it here. Okay. All right, this is the basic problem. If I'm looking at this as a bird's eye view, it looks like this, and the current goes this way. All right. But it's also important to note that this is the electron current. Okay. So I would say the electron current goes here. which means the positive or conventional current that we like to call, like the real I, right, goes in this direction. But when I say I goes here, when I say 2 coulombs goes there, you have to really remind yourself what's actually moving. And it's the electrons. So that means if I say I goes this way, what I really mean is the electrons are going this way. If that's confusing, remember how we polarize an object. So if I have like, here are a pair of scissors I use, right, when I tailor. And remember what I said, if I bring a positive object on this side, right, and we say this side gets negative, and then and this side gets positive, right? And we model that by saying like positive charges go over here, negative charges go over there. But what really happened to make this side positive? The negative charges went from here to here, leaving this area more positive and this area more negative. But the positive charges didn't really move. I didn't really have positive charges go from here to here, but we modeled it that way. In the same way, when I say, oh, positive current goes this way, what I really mean to say is negative current goes this way, okay? Okay, so part A is really simple, right? If the battery supplies a voltage of 9 volts and the resistor is rated at 2 ohms, what is the current running in the circuit, assuming the wires themselves have 0 resistance, right? And that's simply, right, V as IR. The battery is 9 volts, so the voltage drop across the resistor due to the loop rule is also 9 volts. Solving for the current, and the resistance is 2 ohms. That implies my current is 4.5 amperes. That's a very large current. All right. If you think about how many electrons are passing through the resistor every second, that's a lot. If I have 4.5 coulombs every second, you know how many electrons are in 1 coulomb, right? It's huge. Okay. B. Before the circuit is turned on, the magnetic field is measured to be uniformly 3 Tesla pointing into the page. Okay. Let me draw this for you. Right, so this magnetic field is 3 Teslas before the circuit's turned on. All right. Why do I have to specify before? Because when we turn it on, I would expect this field to change, right? Why should the field change? Because when I have current going through this circuit, right, this blue part of the circuit, right, that current and that moving charge creates its own magnetic field. And how do I find the resultant field? I just add the 2 vectors together, right? Thank you for answering the question, Chris. I like how you never take my questions as rhetorical. I like that, okay? I like when you answer questions, everybody. The resultant field at point A will be less than or greater than the resultant magnetic field at point B. Right, so it's basically asking, is the resultant field here going to be larger than 3 Teslas, and over there, is it going to be larger or less than? And we have to use the right-hand rule, except this time, because we're talking about the electron current, we're using our left hand, okay? So let's look at here. Oh, the field inside here points into the page. Or if I want to use my right hand, I can. But if my electron current goes this way, I have to talk about my positive conventional current going this way. And if I use my right hand, I'll still say it goes in, right? So the field due to the blue current, right, I would say goes in. And on this side, it goes out. So everywhere in here, right, it goes in. All right. So on this side, my magnetic field would point into the page, and it'll be greater than 3 teslas. On this side, I don't know. You might be inclined to say, oh, the field here will decrease and it'll be less than 3. But what if the blue field is larger than 6 teslas? Then it would be greater than 3 pointing out of the page, right? So I don't really know, right? So, but it's safe to say it could decrease because it's extremely hard to generate a field that's greater than 3 teslas with just 4.5 amperes. Okay. Actually, no. It's more than possible. I'm sorry, but I don't know. Okay, because I haven't taught you the formula, have I, for the field generated by a current carrying wire. And we're not going to learn it either. It's not important. Oh, my toe! All right. So part C asks if the circuit has a width of 10 centimeters. Okay. Remember, the length can change. So what am I saying here? I'm saying this is 0.1 meters. The length of the circuit, I don't know. It's going to change as the bar moves. Why do I know the bar is going to move? Well, if I have a negative charge going up and the field points down. Wait, I thought you said you don't know if the field points down or up. Dude, these moving charges will not feel their field. They don't feel the blue field. So the only field that these moving charges in this circuit experience is the original raw 3 Tesla field. Why did you even ask the question about whether it's greater than or less than 3 Teslas? Because I wanted you to get some practice with the right hand or left hand rule. And like the concepts of like adding resultant fields and stuff, right? And now this is an additional exercise about recognizing that, hey, a charge never feels its own field, right? So these moving charges will only feel the external 3 Tesla field, all right? So that points 3 Teslas down. My electron's going up, so the forces are going this way, all right? So that means that this bar experiences a force this way. And this is basically how, on a very basic level, how a railgun works. It's an electronically powered projectile launcher that uses a magnetic field. Yeah, it's pretty cool, right? There's no gunpowder, there's no explosives, there's no elastics, there's no spring cannon. It's just an electromagnetic propulsion system like this. And so then the hard thing is it's really important that there's low friction between this bar and this part of the circuit, but it's also important to maintain good contact so the current can run through, right? So the larger the field, right, because I know the force is the current times the length times, so there's 2 ways to increase the force on that wire. One is to increase the current, and the other is to increase the magnetic field. What is the force? Well, it's the length, which is 0.1. Whoa, Mr. So, I thought you were only, how do you know how long this is? Well, I'm only using 0.1 meters because that's the only section where the force is applied. Right? Here, there's nothing. There's no current going through here. There's no current going through there, right? So why do I include that in my length? I don't. Yeah, and then if I do that, then the magnetic force happens to be around 1.35 newtons. If I plug in all the numbers, right, because this is 4.5 amperes, 0.1 meters, and then this was 3 Teslas. So the force ends up being around 1.35 newtons, okay? Now, part C2 asks, how long will it take to reach a speed of 50 meters per second if it starts from rest, right? Well, I have to remember from the problem that the bar had a mass of 25 grams, right? And then I just say, well, F is ma. Cool. And the net force. What's the net force? It's the magnetic force. Bird's eye view. There are two other forces. There's a gravitational force and a normal force. They cancel, right? So the free body diagram from the side view looks like this: Fg, Fn, Fb, friction. Let's ignore friction, okay? Yeah. So then I have 1.35 newtons equals 0.025 kilograms times my acceleration. My acceleration is 54 meters per second squared. Is it? That seems small. No, that seems right. My initial velocity is 0. My final velocity is 50 meters per second. Boom. It takes around 0.93 seconds, right? So you can see from this very basic railgun, it only takes less than a second to reach 50 meters per second, right? That acceleration could have been a lot more if I decreased the mass of that projectile. But then, like, you have a very light projectile that's like susceptible to air resistance and stuff, and won't make a lot of impact when it collides with something, right? And I hate going over military applications of stuff like this. The railgun is not the only militaristic, it's not the only application of like this kind of technology, right? Like this can be used to launch anything. Magnetic propulsion systems are basically how we accelerate particles when we talk about particle accelerators and forcing protons and electrons to collide with each other at like 0.999 speed of light, like in the LHC, the Large Hadron Collider. It does not work like this, but it does uses magnets to accelerate objects and stuff. Okay, cool. Now, if I'm going to timestamp this at what is this, 23.5 minutes? No, like 23:45. We're going to talk about, I think, a really important question, and about magnets. Right, so we talked about moving. So I want to talk about magnetic field. What is it? What's the source? We said moving charges and magnets themselves. All right, what do they affect? Well, they affect moving charges. And they affect magnets. Right? Remember they align. Right? Magnets will always like rotate to align to the external magnetic field. That's how a compass works, right? A compass is just a very simple magnet. They also affect certain metals. Right? You'll notice a magnet can pick up some metals and it won't pick up other metals, right? That's a pretty cool observation. And these metals are iron, nickel, and cobalt. And only these metals, all right? They're very special, okay? Just like you, they're stars. Who's a star? Everyone, let me see some stars in the chat, please. I'm going to type 1, 2, because you guys are stars. You guys are stars for waking up this way every morning, doing your work, coming in to learn. I appreciate it. Okay. You guys give me a reason to wake up. Okay. So, nice star, Kyle. not. You type in the emoji keyboard. So you click on that smiley face at the very bottom, and then you can like search for emojis. And you can search star and stuff. Okay, well, let's go back to this. What is a magnet? Right, we have a basic bar magnet. It has a north and a south pole. The field around it looks like this. Right, that reminds us of the field due to a loop of current that looks basically identical. Right? And basically many loops stacked together look almost even more like the bar magnet, which kind of hints that these are all related in some way. The other way I can think about a bar magnet is if I bend it, I can get a horseshoe magnet. So some of us have seen magnets like this. What's the point of a horseshoe magnet? It's not to like make a cool looking magnet. It's simply to, first of all, how does the field look like for this one? It looks like this. I still have this very basic thing where the field points from north to south. And magnetic field always comes out of a north pole into a south pole. But more importantly, in the region inside the horseshoe magnet, I get a field of uniform field. I get a region of uniform field, and that has a lot of useful applications, like our example problem from last night. Okay. Okay. So here is the big kicker. How do natural elements function like magnets if there's no current running in them, if they're not hooked up to a battery and stuff? Well, you got to look inside at let's look at an electron. Here's an electron. It's much bigger than a real life electron. Electrons, the way we model them currently, they don't just sit around, right? They spin. They rotate in place. So this electron rotates around this axis, this way. And when an electron spins like this, we say it's basically equivalent to very small electric current going this way. And that in itself forms a very small magnetic field. If I use the right-hand rule, I would say the field goes up inside, but it's a negative charge, so the field goes down. Okay. Right. So the electron spinning has a field just like this, right? But I don't really want to talk about its bell pepper thing. I want to talk about the field line at the very center, right? You'll notice at these magnets, you'll always have one field line that goes straight through, right? And we call that the magnetic moment, right? So the electron's magnetic moment points straight down, right, when it's rotating like this. And when I describe a magnetic moment like this, what I really mean is my eggplant is going to look like this, right? Or my bell pepper is going to look like that, my pumpkin, okay? Whoa, Mr. So, here's the real critical question, right? We're hitting at 31 minutes. If every element has electrons and every electron spins, Why do only certain materials get to act like magnets? Great question, Alex. We're going to answer that right now. In almost every material, all right, electrons come in pairs, all right, and they share a lot of, almost like how Heraclitus would say, there's a unity of opposites, and within these pairs, the electrons have opposite values of everything, right? So they have opposite linear momenta, they have opposite angular momenta, and that includes spin. So if I have one electron and it's spinning this way, and it has a magnetic moment pointing this way, then somewhere else in that material, there's guaranteed to be another electron that's spinning the other way and has a magnetic moment pointing the other way, right? So in almost every material, because every electron is paired up, this is the Pauli exclusion principle, exactly. Right, PEP, Pauli exclusion principle, super important, right, in the study of quantum mechanics and chemistry. They're the same thing. Pauli exclusion principle is a form of entanglement, in that if I know that two electrons are paired up and I observe the spin of one, I have automatically observed the spin of the other one because I know it's opposite. There is a reason for that, but the proof for the Pauli exclusion principle is it's not something we can go over right now. But you should know there is a proof for it, right? So what does that mean? In any random material, if every electron has so like these are paired, has a pair. And though in each pair, the net magnetic moment is 0 because they cancel out, well, this has a net magnetic moment of 0 because all the electrons cancel out. What makes iron, nickel, and cobalt so special is that these are materials that have a significant amount of free agents, right? So they have a lot of electrons that are single and ready to mingle, okay? So which means that it's possible for these materials to have a net magnetic moment. It doesn't guarantee them, right? Because if I have a bunch of single free agents that are not paired, it leaves the possibility that, like, oh, in this material, let's say these cancel, these cancel, these cancel, but I have a bunch of free agents that are unpaired, right? So, like, and they can point anywhere, right? They're not attached to any other electron. If they're randomly distributed, however, I would still say this has no magnetic net moment. That's why, like, this steel pair of scissors, which is part nickel, part iron, and part cobalt, is not magnetic, right? This is non-magnetic because my free agents here are randomly distributed, but they have a possibility to not be. And in reality, when iron cools, okay, how are they free? It's a quantum mechanical property of the material. It's not the material, but the states that are allowed in iron. Something about it allows for the existence of free agent electrons. Yeah, I guess they're like unbound, and in the system, where I'm looking at the sea of electrons in iron, it just behaves a little differently. I'm not really sure. Okay, this is something I asked Mr. Mulek a long time ago too, and it's something so niche that you'd have to really be in that kind of particular field of study to really know. But it's there. When iron cools down, so let's say I have a bar of iron. It'll form like regions like crystals, right? Where chunks of iron molecules, it has a crystalline structure, right? And the size of these crystals are determined by how fast or how slow it cools down from its molten temperature, all right? The cool thing about the way the crystals cool, though, is that within each crystal, most of the free agent electrons are spinning in the same direction. So I have these mini magnets within the metal, right? So maybe all of the free agent electrons in this crystal have a magnetic moment that points up. And all of the magnetic moments in this crystal point to the right. The problem is, within that cooling process, it's still random. So how the heck, bridging indeed needed, how the heck do I turn this into a magnet? Right? Because what I have now is the same thing as this problem, right? When I have crystals, within the crystal, all the free agents turn in the same direction. But guess what? All the crystals are now in random directions. So I still don't have a way to really have a net magnetic moment. But I do. Because guess what? I'm going to place my magnet and my iron bar in a very strong external magnetic field. How do I do that? Maybe I put it in a giant solenoid with a high amount of current, right? And I place my bar magnet inside. Okay, what happens here? All of these moments are going to rotate, right? Every crystal that has all these magnetic moments pointing in the same way that acts like a little magnet are now going to rotate themselves, right, like little compasses, to align themselves so their magnetic moments now point in the same direction as the external magnetic field, right? This is how compasses work. If this field is strong enough, once I turn that field off, that shift will actually become permanent. So I'll have crystals where all of their magnetic moments now point up. And I have a bar magnet now, where this is my north pole, this is my south pole. But what is this really? This is a collection of like 1 trillion electrons all spinning in the same direction. Why are they all allowed to spin in the same direction? Why don't they have others that cancel out? Because they're all free agents, okay? If you don't believe me, here I have a particularly strong magnet. This is a neodymium magnet, and I gotta go to my workstation here. Here are some iron pins that I use when I drape things. So here I have an iron pin, and boom. Hold up, I just gotta find the right spot for this. 1 second. Oh, come on, please. Okay, whatever. So I have this iron pin, right? And why is it sticking? Because in the presence of a magnetic field, what is this iron pin doing? It is now acting like its own magnet, right? And magnets attract other magnets, right? South. So this this pin is now its own. It has a north pole and a south pole, right? As determined by this diagram, north and south. And its north pole is attracted to my original magnet south pole and vice versa. That's why it sticks. But the cooler thing happens here. Here's proof that this pin is now acting like its own magnet, because it can now attract a second pin and turn that pin into a magnet, all right? And here's my proof of showing you that the internal structure of my pin, the crystalline structure, what's happening here is permanent. What I have in my hand right now is a very slightly magnetized pin. This magnet was so strong. Its magnetic field is so strong, I cannot really put it near my laptop, okay, that it permanently altered this random magnetic moments and caused them all to align in the same direction to give my top pin a permanent magnetic field. It's really weak though, all right? So the magnetic field of this top one isn't going to really permanently change the magnetic field of that bottom one, okay? How cool is this, guys? Tell me what the heck? No wows in the chat. What the heck? The first time I saw this, I was like, whoa, right? Dimon says, how do I change my top pin to be a normal pin again? How do I demagnetize it? It's pretty simple, actually. Not too late, guys. I don't care. I don't care anymore. All right, too late. You just bang it around. So if I take this pin, this is my top pin, right? And I like hit it with my scissor. Bam, 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 bam. It won't act like a magnet anymore, right? Oh, it still does. Whoops. So I guess if you bang it hard enough, it'll kind of shake the crystals up, the crystalline structure, and it'll lose its magnetic properties. But I can't bang it hard enough. So right now I basically have a permanent magnet, which is really cool. Because guess what? Oh, this is exciting. Oh my gosh. Oh, oh, oh. So I'm looking for something. I don't know if I have it. Ay, 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 ay. I don't have it. I don't have a cork. All right, but it's okay. Maybe this will float anyway. If I have a needle and I put it in my water. Oh, crap. It won't float. So this is a problem. Not a big deal. I need something that floats. I thought I had a cork somewhere. What the heck? All right, so unnecessary, because guess what? I have some tape. And I'm going to tape my needle to a piece of wood that floats. So now I have a magnetized needle, and it's in my bowl of water. Here. And it should spin and rotate to face north. that's east for me. Yeah, this is working, right? And if I put it here, it's going to spin. Watch how it rotates. It's always going to face the same direction. Yep, it's always going to, because it's a magnet and it's interacting with Earth's external magnetic field. No matter what I do to this, it's, oh, now it's sinking, oh no, right? So the cool way to do this, and I learned this from watching Arthur. I think someone did this on Arthur, right? Once you have a magnetized needle, you stick it in a cork that you can get from drinking wine or whatever, or grape juice, right? And then you have a compass. It's like a really cool, if you're lost in the woods, you can do this in a creek or whatever, yeah. So, yeah. Isn't that cool? So, how do permanent magnets work? What are permanent magnets? Right? Everything is just moving charges, right? Or spinning charges, right? And why do certain metals get to have a net magnetic moment? Because we went over, those are the only 3 metals that have like free agent electrons and stuff. And when I have enough free agent electrons and they're forced to all point in the same direction, then I have a net magnetic field, right? So to magnetize a metal, it needs to be exposed to an external magnetic field first, right? That's what we went over here. And that's basically how basic electromagnets work and stuff. Yeah. Right. So that basically wraps it up. So today we went over the Railgun example. We went over the source of magnets and like how it really works. I hope that was really interesting for you. Tomorrow we will be answering a critical question about how to use magnetic field to generate electric current. And we're going to be because we basically looked at the backwards one, right? We know electric current generates magnetic field. Is the backwards possible? Yes. And it's basically the basis of how almost all power plants work, right? So if you're curious as to like what's the difference between hydroelectric power, solar power, wind power, fossil fuel power and stuff, we're going to learn about that tomorrow, right? Binky's a bulldog. I thought that was clear. That's why he's also like a bull, like big. For the most part, a lot of them share their first letter with the animal. So Buster's a bunny, Arthur's an aardvark, Muffy's a monkey, Francine's also a monkey, but you know I said mostly. Binky's a bulldog. Brain is a bear. Although since he's Arthur's cousin, I guess he's also an aardvark. What's Penelope? Maybe Penelope's a pangolin. I have no idea. Right? Mr. Ratburn is a rat. Sue Ellen. Oh, I was really shipping Sue Ellen and Arthur pretty hard. Never happened though. Sue Ellen would be, I don't know. Yeah, she just looks like a person. They all look like people, right? They're anthropomorphic. So yeah, so tomorrow we're going to be going over how magnetic field generates electric current and how power plants work. And I think it has like a lot of deep implications for how everyday life works. No practice today, guys. Just, I want you to understand how this works because I think it's cool. Okay? Have a great day. Bye. See you tomorrow.